Hello my friends and welcome back to the You Can Do TV channel.
The construction of the Aasta Prima, a 300-meter Hyperion-class cruise ship, was a complex engineering feat undertaken at the Mitsubishi Heavy Industries (MHI) shipyard in Nagasaki, Japan. This vessel was the first in its class to incorporate the Mitsubishi Air Lubrication System (MALS), a technology designed to enhance fuel efficiency by generating a microbubble layer beneath the hull. This thin layer of air reduces friction between the ship and seawater, leading to a measurable reduction in fuel consumption and a decrease in carbon dioxide emissions by approximately 7%. The integration of this system required precise adjustments to the hull design and extensive testing to optimize its effectiveness in varying maritime conditions. Beyond hull efficiency, environmental considerations played a central role in Aasta Prima's design. A multi-stage filtration system was developed and installed to limit the emission of pollutants, such as soot particles, nitrogen oxide, and sulfur oxide. The installation process required the coordination of multiple engineering teams to ensure compatibility with the ship's existing power systems. The ship is powered by three Mach 12 volts M43C main engines, supported by a Mach M46DF dual-fuel engine, enabling it to operate on liquefied natural gas, LNG, marine diesel oil, or heavy fuel oil. This flexibility allows for compliance with evolving emission regulations. Additionally, three diesel generators equipped with Rheinmetall manufactured pistons were installed to provide auxiliary power, requiring careful integration into the overall propulsion framework. Aasta Prima's maneuverability was significantly enhanced through the installation of two Azipod XO propulsion units supplied by ABB. These electrically driven pods can rotate 360 degrees, eliminating the need for traditional shaft-driven propellers. Their installation required precise alignment with the vessel's electrical and control systems to ensure optimal performance. The Azipod system allows for smoother navigation in crowded ports and challenging waters, improving the vessel's overall efficiency and responsiveness. Throughout the construction process, numerous contractors contributed specialized expertise to different aspects of the vessel. Sant Sandelin, in collaboration with Naval Interior Team (NIT), provided the engineering blueprints for passenger staircases. These staircases had to meet strict structural and safety standards while complementing the ship's overall design. Manufacturing and installation processes were meticulously coordinated to ensure compliance with international maritime regulations. The ship's interior accommodations required an efficient use of space without compromising passenger comfort. Rans Fertig supplied high-end convertible sofa beds for 900 cabins and 32 suites, integrating space-saving functionality with durability. The installation process involved precision measurements and quality control assessments to ensure seamless integration within each cabin layout. A critical aspect of the ship's safety design was fire protection. Elematic played a key role in developing fire-resistant compartmentalization using digital modeling tools such as Nupus Kidmatic and MHI Mate software. The process involved mapping fire zones, determining optimal placement of fire-resistant barriers, and ensuring that escape routes were strategically positioned. These safety measures were essential in meeting international fire safety regulations and protecting passengers and crew in the event of an emergency. Beyond fire safety, Elematic also contributed to the design and layout of the ship's spa area. While primarily focused on structural and engineering elements, the team worked to balance aesthetic considerations with functionality, ensuring that plumbing, ventilation, and safety systems were seamlessly incorporated into the final design. The five-bladed controllable pitch propellers for the 386-meter patrol boat undergo a precise manufacturing process, beginning with computer-aided design for optimal hydrodynamics. Each blade is cast from high-strength alloy, then CNC machined for accuracy. The hybrid drive integration and modular hydraulic components are assembled and rigorously tested to ensure efficiency and longevity. The transformation of the MS Amara is a feat of engineering precision, requiring seamless coordination across multiple locations. Originally built in the late 20th century, the cruise ship undergoes a critical upgrade to enhance its maneuverability, a process that begins in Hamburg, Germany, with Becker Marine Systems. Following the design phase in Hamburg, production shifts to Vigo, Spain, where some of the most advanced rudders in the world are crafted. Here, steel plates up to 35 millimeters thick are meticulously shaped, welded, and inspected. Quality control is paramount, with every component subjected to rigorous testing. The rudder trunk, a crucial link between the steering gear and the rudder, undergoes extensive scrutiny before its final acceptance test. Weighing over 6 tons, these structures are painted and carefully prepared for transport. Any miscalculation could result in costly delays. The construction of the Type 45 destroyer is a complex and highly coordinated process, requiring meticulous planning and precision engineering across multiple shipyards. Built at BAE Systems' Govan and Scottstown shipyards in Glasgow, Scotland, and Portsmouth, England, the vessels are assembled in large modular sections before being integrated into a fully operational warship. Production begins with cutting the first steel plates, marking the start of a 55-month journey that involves 2.3 million man-hours and 8,000 tons of materials. The ship is constructed in blocks. Govan Shipyard produces the stern to the helicopter hangar, Block A, while Scottstown constructs the central sections housing the Rolls-Royce WR-21 gas turbines, Block BC, and the bridge, Block D. Portsmouth Shipyard fabricates the bow, Blocks EF, masts, and funnels. For ships 2 through 6, these blocks are assembled at Govan before being transported to Scottstown for final integration. Once the hull is completed and launched into the Clyde, the ship undergoes a critical outfitting phase. Advanced radar systems, missile equipment, bow-mounted sonar, and propellers are installed, along with the 4.5-inch main gun. The vessel's integrated Sea Viper air defense system and Samson radar are then tested. Quintrex plate boats feature a robust hull structure, utilizing up to 6 mm marine-grade aluminum for the bottom sheets and 4 mm for the topsides. The construction begins with precise cutting and shaping of aluminum plates, which are then welded together to form the hull. The HDR hull design, developed through extensive research, incorporates refined planing strakes and an optimized center of gravity for enhanced performance and stability. A defining aspect of the build process is the interlock core system, which includes 2 full-height stringers and 8 full-length one-piece stringers with interlocking gibs. This configuration significantly enhances the hull's structural integrity, ensuring durability in harsh offshore conditions. Additionally, the Marine Corps construction method employs an internal subframe with a lattice of longitudinal and latitudinal ribs, reinforcing the hull and shaping its form. The structure is further strengthened with vertical stringers, 6 mm thick, and horizontal ribs, 5 mm thick, topped with a fully welded plate floor. To maximize safety and functionality, each boat is equipped with an auto-drain deck featuring a sealed, no-return scupper system. This mechanism directs excess water through a rear gutter into a lower chamber, where it is efficiently pumped out. Separate from the underfloor bilge pump, this system provides an additional layer of protection against water accumulation. The hull's critical components, such as the keel and chines, are not only welded but reinforced with 4 precision welds executed by skilled technicians. This advanced welding approach ensures maximum strength and longevity. Upon completion of the structural elements, the boat undergoes final assembly, including the integration of the checker plate floor for durability and skid resistance. Additional features, such as EVA matting for comfort and noise reduction, are fitted according to model specifications. Each boat is rigorously tested to meet industry standards before leaving the factory, guaranteeing superior performance on the water.
Launch of Aasta Hull 396 Queen Beetle. In April 2020, the launch of Aasta Hull 396, named Queen Beetle, was facilitated using the SPMT from Aastal's Henderson South shipbuilding facility. This high-speed trimaran ferry, designed for Junior Kyushu Beetle of Japan, measures 83 meters and is built to transport 502 passengers between Fukuoka, Japan, and Busan, South Korea, at speeds of 37 knots. The SPMT played a critical role in this process. These transporters drove under the vessel, lifting and securing it for transport to the launch site. The remote control capabilities of the SPMT, with its comprehensive TFT display, allowed operators to manage all transport functions efficiently, ensuring smooth and precise movements. Axle compensation ensured the ferry was transported over uneven surfaces without risk of damage. The slope adjustment feature enabled the SPMT to maintain stability while navigating any inclines, ensuring the ferry remained level. The coupling functionality of the SPMT modules allowed for the assembly of the required configuration, providing the flexibility needed for this complex transport operation. The construction of the Aasta Hansteen offshore platform is a monumental engineering feat, marking one of the largest and most complex industrial projects in Europe. Located in the Norwegian Sea, 300 kilometers from the coast of Norway, the Aasta Hansteen gas field is situated at a water depth of 1,300 meters, making it one of the deepest field developments on the Norwegian continental shelf. Design and construction. The Aasta Hansteen platform is a spar type, the first of its kind on the Norwegian continental shelf. A spar platform consists of a large diameter, vertical cylinder supporting a conventional deck for drilling, production, and accommodation facilities. This design allows for stability and storage of condensate in the hull below sea level, which can be offloaded to shuttle tankers. The platform's production and export risers are steel catenary risers, SCRs, which are utilized for the first time in the Norwegian Sea. The spar hull was designed by Technip, while the topsides were designed by CB&I. Both components were fabricated by Hyundai Heavy Industries in Ulsan, South Korea. The spar hull measures 198 meters in height, of which 177 meters are submerged, and has a diameter of 50 meters, making it the largest spar platform ever built in terms of diameter and displacement. Transportation and installation. Construction of the Aasta Hansteen spar was undertaken in a dry dock where it was built on its side on barges. Once completed, it was floated off the barges and onto the heavy transport ship, Dockwise Vanguard, for transportation to a fjord near Stord in western Norway. The spar was then upended in the fjord, and the topsides were installed using the float-over technique. This innovative method involves floating the topsides onto the hull and securing them in place, reducing the need for heavy lift vessels. After the topsides installation, the platform was towed vertically to the Aasta Hansteen gas field, located 300 kilometers off the coast of Bodø. It was anchored to the seabed using 17 polyester mooring lines, each 2,500 meters long, ensuring stability in the harsh Arctic conditions. Operational features and connectivity. The Aasta Hansteen platform began production on December 17, many years ago. It processes gas from the Lova, Hackling, and Snefrid gas fields, with future fields expected to be tied back to the platform. The produced gas is exported through the Polarod pipeline, a new 480-kilometer gas pipeline that connects the platform to the Nyhamna processing plant on the Norwegian coast. The Polarod pipeline not only facilitates the export of gas from Aasta Hansteen but also provides infrastructure for other fields in the Norwegian Sea. For the Viet Suvi Petro Thien Ung project in Vietnam, Boskalis achieved a remarkable feat by installing the Thien Ung BKTNG 4,200 metric ton mount, topside and 850 MT living quarters using the sheerleg Asian Hercules 3. This installation represents the world's heaviest lift of a topside by a sheerleg in an offshore environment to date. Floating sheerleg cranes are versatile and cost-effective solutions for heavy lift projects, and Boskalis owns a fleet with lifting capacities ranging from 400 to 5,000 tons. These cranes, often equipped with their own propulsion systems, specialize in heavy lift activities requiring advanced engineering skills. Unlike other crane vessels, floating sheerlegs cannot rotate their cranes independently of their hulls. The installation process began with detailed engineering work, including lifting analysis, rigging design, and mooring analysis. Preparation and mobilization of the Asian Hercules III, a 5,000 MT sheerleg operated by Asian Lift, a joint venture between Boskalis and Keppel, followed. The operation required setting up an anchor pattern and coordinating with transport barges. On the 21st of September, the 4,200 MT topside was successfully lifted and installed onto a pre-installed jacket in the Nam Khan Sun Basin at a depth of 120 meters. This was followed by the installation of the 850 MT living quarters on the 24th of September in same year. The project, executed on a fast-track timeline to avoid the monsoon season, marked the first offshore project for the Asian Hercules III. The project was completed without incident, adhering to the NINA, no injuries, no accidents, initiative. Manufacturing a wind tower involves several critical stages, each ensuring the structural integrity, durability, and efficiency of the final product. Below is a detailed description of the process, focusing on the key steps: bending, welding, flashing, and painting. The first step in manufacturing a wind tower is the bending of steel plates, which form the primary material for the tower. These plates are typically made from high-strength, low-alloy steel, providing the necessary durability and flexibility. The bending process begins with cutting the steel plates to the required dimensions using CNC plasma or laser cutting machines for precise measurements. Once the plates are cut, they are fed into a rolling machine. This machine consists of a series of rollers that progressively bend the flat steel plates into a cylindrical shape. The rolling process requires careful control to ensure that the curvature of the plates is consistent and meets the specified dimensions. The plates are often bent in sections, with each section forming a segment of the tower. These segments are later joined together to form the complete tower structure. After the bending process, the rolled steel segments are welded together to create the tower sections. This stage is crucial for ensuring the structural integrity and stability of the wind tower. Welding is typically performed using submerged arc welding, SAW, which is known for its deep penetration and strong welds. The welding process begins with aligning the edges of the bent steel plates. Automated welding machines then move along the seams, applying a continuous weld bead to join the segments. Multiple passes may be necessary to ensure a robust and defect-free weld. To guarantee the quality of the welds, non-destructive testing methods such as ultrasonic or radiographic testing are employed. These tests help detect any potential flaws or discontinuities within the welds, ensuring the structural soundness of the tower sections. Once the welding is complete, the tower sections undergo a process known as flashing. Flashing involves grinding and smoothing the welded seams to remove any excess material or irregularities. The painting process begins with surface preparation, which involves cleaning the tower sections to remove any contaminants, oil, or rust. This is typically done through sandblasting or abrasive blasting. Once the surfaces are clean and free of debris, a primer coat is applied. The primer acts as a base layer, enhancing the adhesion of the subsequent paint layers and providing additional corrosion protection. After the primer has cured, multiple layers of high-performance industrial paint are applied. These paint layers are typically formulated to withstand extreme weather conditions and provide long-lasting protection. The painting process may also include the application of specialized coatings, such as anti-fouling coatings for offshore wind towers, which prevent the buildup of marine organisms. At the Port of Rotterdam, the loading and transportation process involves meticulous coordination and the use of two of the world's largest crane brands, the CC 8800, with a capacity of 1,600 tons, and the CC 6800, with a capacity of 1,250 tons. Recently, 480-ton wind turbine transition pieces arrived from Antwerp and are ready for load-in on the quay. Once off the barge, the Blue Saren's TP handler, mounted on SPMTs, takes over. This handler efficiently picks up and maneuvers the transition pieces to the laydown area, placing them gently on concrete foundation blocks. The barge then rotates to allow the cranes to access the remaining pieces. These wind turbine parts, destined for the North Sea, include yellow transition pieces from Antwerp and brown and white monopiles manufactured in Rotterdam. Each transition piece is paired with a corresponding monopile before being transported offshore. The monopiles, weighing approximately 1,088 tons each, are lifted in tandem by the CC 8800 and CC 6800 cranes using long slings to prevent damage. With the monopiles secured, the CC 8800 crane lifts the transition pieces onto the barge, readying them for their journey to the North Sea wind farm. Transporting a 590-ton offshore tripod using SPMT in open compound. The self-propelled modular transporter, SPMT, is essential for the transportation of a 590-ton offshore tripod in an open compound. These heavy-duty modules drive under the tripod, lifting it with precision and minimizing downtime. The use of pallets or heavy-duty feet enables the SPMT to effectively manage and transport the immense structure. The 2,430 mm outer width of the SPMT allows it to be transported cost-effectively in standard flat-deck containers, avoiding the need for special permits and additional costs. With an ergonomic radio remote control, operators can easily manage steering, driving, lifting systems, and brakes, ensuring the safe and efficient movement of the tripod. Axle compensation ensures even pressure distribution, allowing the SPMT to maneuver over uneven terrain without causing ground damage. The coupling capability of SPMT modules provides flexibility, enabling the assembly of desired combinations for heavy transport efficiently. Transporting a 212-ton upright tower segment. Transporting a 212-ton upright tower segment using the SPMT showcases the versatility and efficiency of this modular transporter system. The SPMT drives under the tower segment, utilizing its lifting capabilities to securely hold and transport the load. The ergonomic radio remote control, featuring a 35-inch TFT display, allows operators to manage all functions, including steering and lifting, with precision. The remote's lightweight design ensures ease of use. Axle compensation is crucial in this operation, as it distributes pressure evenly across all axles, allowing the SPMT to navigate inclines and uneven surfaces safely. The slope adjustment feature, powered by the PPU's tilt cylinders, maintains platform levelness during transport on sloped terrain. Coupling and uncoupling SPMT modules enable the efficient assembly of the necessary configuration for the task, ensuring flexibility and adaptability. The standardized coupling units streamline the process, facilitating quick and reliable adjustments to the transport setup.
The TDRI aluminum boat welding system integrates advanced robotics and automation to enhance the precision and efficiency of aluminum boat manufacturing. The process begins with offline programming using robotics' specialized software, which allows welding paths to be pre-planned before production starts. This minimizes downtime between product changes, as the system is ready to execute welding tasks without additional manual adjustments. Once the program is loaded, seam tracking is managed by the FujiCam system, which is integrated with the FANUC ARCMate_100ID_10L robotic welder. This ensures that welds are placed with extreme accuracy by continuously monitoring the joint's position and making real-time adjustments. Unlike traditional methods that require manual intervention, this system autonomously aligns the welding torch to maintain consistency. For proper positioning of both the welding robot and the boat structure, the system employs a high-precision gantry and positioning equipment. This setup stabilizes the aluminum components, preventing misalignment during welding. The welding process then proceeds with programmed movements, ensuring uniform penetration and reducing defects. By automating both seam tracking and positioning, the TDRI system eliminates inconsistencies in weld quality while improving production speed.
Now, let's find out how Tideman Boats manufactures high-density polyethylene HDPE hulls. The process begins with CNC cutting HDPE sheets into precise shapes for hull components. These cut pieces are then thermally welded using high-temperature fusion welding techniques, creating seamless and ultra-strong joints that eliminate weak points. Once the hull structure is assembled, additional reinforcements are integrated to enhance rigidity and impact resistance. Internal compartments, such as buoyancy chambers, are incorporated to optimize flotation and stability. Unlike traditional metal or fiberglass hulls, HDPE requires no painting or anti-fouling treatments, significantly reducing production time and environmental impact. After welding, the hull undergoes stress testing and quality checks to ensure structural integrity. The final stages include outfitting the boat with necessary fittings such as engine mounts, seats, and safety features.
The LSAM 3D printed marine boat hull pattern is manufactured using Tecmer Electrofill copyright ABS LT13DP, employing advanced additive manufacturing technology. LSAM systems integrate both printing and trimming on the same machine, utilizing a fixed table with high walls and a moving gantry. Machines like the 1010 feature a single control system, while larger models, such as the 1020 and beyond, operate with dual gantries, allowing simultaneous printing and trimming. The process supports vertical layer printing, enabling the creation of structures as tall as the machine table is long. With a maximum processing temperature of 450 degrees Celsius, these systems accommodate a wide range of composite polymers. Fume extraction with activated charcoal filtration ensures a controlled production environment, enhancing efficiency and precision. Sea hunt boats are crafted with precision, beginning with the raw fiberglass materials that form the foundation of each vessel. The production process starts with hull molding, where fiberglass sheets are layered with resin inside a custom-designed mold. The application of gel coat ensures durability and provides a variety of vibrant color options with UV inhibitors. Once the hull is set, the boat moves to structural assembly. The stringer system, a critical component for strength and stability, is bonded to the hull using advanced composite materials. This stage ensures maximum durability while maintaining the lightweight structure necessary for optimal performance. The true Carolina bow flare is crafted providing superior handling, stability, and a dry ride. In the tooling shop, in-house engineers continuously refine and test new designs to ensure each model meets industry standards. The deck and hull are then joined using high-strength adhesives and mechanical fasteners, forming a seamless, water-resistant structure. Next, the finishing process incorporates entertainment and comfort elements. Upholstery, available in premium options, is installed along with customized features like Corian countertops, freshwater sinks, and ample storage solutions. The T-top and leaning posts receive powder coating in selected finishes. Final assembly includes wiring and electronics installation, featuring Garmin navigation systems for enhanced functionality. Quality control testing is rigorous, ensuring every sea hunt boat meets strict safety and performance standards before leaving the factory. Pioneer boats are manufactured using rotational molding, a process that ensures durability and sustainability. The construction begins with the selection of high-quality linear low-density polyethylene, LLDPE, a material known for its strength, flexibility, and recyclability. First, a metal mold is prepared and coated with a release agent to ensure smooth demolding. The mold is designed to form the boat in a single, seamless piece, enhancing structural integrity. Next, a precise amount of polyethylene powder is placed inside the mold. This ensures consistency in thickness and material distribution across the boat's structure. The mold is then heated in a large rotational oven while simultaneously rotating on 2 axes. This allows the polyethylene powder to melt and evenly coat the interior surface of the mold, forming a hollow, impact-resistant hull. After achieving the desired shape, the mold is gradually cooled to solidify the structure. Once cooled, the boat is carefully removed from the mold without requiring seams or joints. Excess material is then trimmed, and necessary fittings such as seats, handles, and motor mounts are installed. The boats undergo rigorous quality control inspections to ensure structural strength and uniformity. Pioneer boats are designed for longevity and minimal maintenance, making them a sustainable choice. At MV Werften, Germany, engineers integrate ABB's automation and azipod propulsion into 5 genting vessels, refining efficiency. Early on October 20th, MSC Magnifica entered Dock 8 at Damen Ship Repair Rotterdam for an extensive overhaul. Before docking, engineers positioned hundreds of dock blocks to support the hull once the dock was drained. As the ship settled, crews connected an external water supply to cool auxiliary engines, ensuring utilities for 700 crew members on board. Immediately, scaffolding was erected, and workers began cutting and replacing 40 tons of corroded steel plating, welding new sections into place. Simultaneously, a 24/7 painting operation commenced, removing old coatings and applying protective layers over 6,000 square meters of the ship's surface. In the mechanical workshop, technicians dismantled the worn rudder systems, machining the rudder stocks to precisely fit newly fabricated components. Lifeboats were hoisted off for inspection, while stabilizers and thrusters underwent maintenance. After precise alignment and installation of the new rudders, anti-fouling coatings were applied, propellers polished, and final checks completed ahead of schedule, preparing MSC Magnifica for departure. On July 11, 2011, the Miss China, a 67-foot former commercial fishing boat, was systematically dismantled in New Bedford, Massachusetts. Before destruction could begin, all hazardous materials, including residual fuel and oil, were extracted to prevent contamination. Salvageable components, such as rigging, wiring, and metal fittings, were removed for resale or recycling. The first step in the physical demolition involved lifting the Miss China using a 400-ton marine travel lift. The boat was hoisted into the air by heavy-duty slings and carefully lowered into a hopper barge positioned underneath. Once in place, the vessel was secured with boat stands to prevent movement during transport. A tugboat then towed the barge to a designated demolition site just north of the Route 6 swing bridge, where an excavator equipped with hydraulic shears awaited. Upon arrival, the demolition team, led by Johnny Roy and assisted by his brother Conrad Jr., began dismantling the ship in stages. The excavator operator started by stripping away the fiberglass coating, which had been applied over the wooden hull. As the shears cut into the fiberglass, large sheets peeled away, exposing the aging wooden frame beneath. The outer layers were systematically removed section by section, allowing the team to access the vessel's internal structure. With the hull exposed, the excavator moved on to dismantling the wheelhouse. Care was taken to remove valuable components, such as the ship's wheel, which was set aside for salvage. The machine then tore into the wooden framework, reducing it to splintered debris. Pieces of the ship fell into the barge below, where workers sorted through the wreckage, pulling out reusable materials like brass fittings and copper wiring. Scrap metal was collected separately to be sold for recycling, while the remaining wood was gathered for disposal. As the demolition progressed, the excavator operator shifted focus to the ship's hold, where the fuel tanks and heavy machinery were located. Using precise movements, Johnny Roy maneuvered the shears to cut around the tanks, ensuring they could be safely lifted out without spillage. Once detached, the tanks were hoisted from the wreckage and placed onto the barge for proper disposal. Next, the ship's generator and engine were extracted. The excavator's claw reached deep into the hold, gripping the heavy machinery and lifting it from the structure. The generator, still intact, was set aside for possible reuse, while the engine, long beyond repair, was designated for scrap. Meanwhile, workers continued sorting through the debris, occasionally uncovering personal items left behind by the boat's former owner. By the end of the process, the Miss China had been reduced to a pile of wooden fragments, scattered metal, and discarded fiberglass. The remaining debris was transported to Maine, where the wood was incinerated as fuel.
Sea fastening. The first step involves sea fastening, which secures the PIF and other necessary equipment to the installation vessel for safe transport to the offshore site. Installing the pile installation frame, PIF. Upon arrival at the installation site, the PIF is carefully deployed. The PIF is engineered to be highly adaptable, capable of being leveled horizontally using its 4 individually adjustable legs. This adjustability is critical to ensure precise placement, especially on uneven seabed surfaces. Leveling the pith. The pith leveling process involves the following key features. 1.5-meter extendable mud mats. These mats extend to provide a stable base on the seabed, distributing the load and preventing excessive sinking into the seabed. Max 3.6-degree local rotation angle of mud mats. This feature allows the mud mats to rotate locally, accommodating minor seabed irregularities. Pith can be set on a max 2.4-degree slope diagonally. The frame can be adjusted to a diagonal slope of up to 2.4 degrees, ensuring that it can be leveled even on sloping seabed surfaces. Leveling and cutting sea fastening. Once the pith is in position, sea fastening is cut to allow the frame to extend shims, which guide the pile during installation. These shims ensure that the pile is positioned accurately and securely. Extending and retracting shims. Shims are extended to guide the pile into place. After the pile is positioned correctly, the shims are retracted to allow the pile driving hammer to pass through and drive the pile into the seabed. The installation of the foundations for an offshore wind farm is a complex and precise operation that involves several key steps and specialized equipment. One of the crucial components in this process is the pile installation frame, pith, designed and engineered by Seaway Heavy Lifting, which plays a vital role in ensuring the correct positioning and stability of the foundation piles. Measuring pile height and top of pile elevation. Precise measurements of the pile height and the top of the pile elevation are taken to ensure that the pile is driven to the correct depth. This step is critical to ensure an acceptable fit for the jacket installation, which is the next phase in constructing the wind turbine foundation. Removing the pith. Once the pile installation is complete and verified, the pith is carefully removed. The accurate installation of the piles provides a stable and secure foundation for the wind turbine structures. "16 years ago, an idea scribbled on a napkin has transformed into the world's first floating wind farm, located off the coast of Scotland. This pioneering project, comprising 5 enormous floating wind turbines, represents a significant leap forward in renewable energy technology and aims to demonstrate the feasibility and benefits of floating wind turbines. The journey began with the construction of a full-scale demonstration version off the Norwegian west coast. This initial model faced considerable skepticism, but it outperformed expectations, providing essential data that paved the way for the current development. The success of the demonstration model underscored the potential of floating wind turbines and set the stage for larger-scale projects. Hywind Scotland is now putting this concept to the test in a park configuration. Within a year, 5 wind turbines will be visible on the horizon. These turbines, connected by submerged cables, will supply power to 20,000 homes in the UK. A key distinction between these floating turbines and traditional bottom-fixed turbines lies in their floating substructures. These substructures were constructed by Navantia in Spain and are integral to the project's success. Measuring over 90 meters in length with a diameter of 14.4 meters, each substructure weighs approximately 3,500 tons. The towers, also fabricated in Spain, were transported to Norway, where the turbines were assembled piece by piece. The capacity of each turbine has been significantly increased from the initial 2.3 megawatts to 6 megawatts. As the turbines were assembled in Norway, each component of the Hywind puzzle arrived and was meticulously put together. These turbines are anchored to the seabed using mooring lines connected to the suction anchors, ensuring stability and efficiency. The heart of the Hywind concept is the floating motion controller, which stabilizes the turbines and enhances power production by adjusting the blade pitch to reduce motion. This innovative technology is crucial for maximizing efficiency and ensuring the reliability of the turbines in harsh offshore conditions. In mid-July, the first turbine was towed to Scotland, with the remaining 4 following shortly thereafter. Once in place at Buchan Deep off Peterhead, the turbines were connected into a grid and underwent rigorous testing before being handed over to operations. This milestone marks the first time such technology has been implemented on this scale, underscoring the groundbreaking nature of the project. The Nordsee 1 offshore wind farm, OWF, project, located in the German North Sea, is a significant milestone in renewable energy infrastructure. A critical part of this project is the installation of the inner array grid cables, an intricate process that ensures the efficient transmission of electricity generated by the wind turbines to the shore. This complex task was executed by the leading seam cable installation duo, the Seam Amory, cable lay vessel, CLV, and the Seam Moxie, installation support vessel, ISV. These vessels were crucial in facilitating the seamless deployment, laying, and protection of the submarine cables. The installation spread for the Nordsee 1 OWF comprised 2 specialized vessels, each equipped with advanced technology to handle the demanding task of submarine cable installation. ISV Seam Moxie. The Seam Moxie is an Ulstein SX-163X bow installation support vessel. It played a pivotal role in the deployment of pull-in, termination, and testing equipment. The vessel is renowned for its award-winning innovative, 3D, motion-compensated crane, which is mounted on the vessel's centerline. This crane is man-riding capable, allowing for the safe and efficient transfer of personnel and equipment. Pre-lay inspection survey. The installation process began with a pre-lay inspection survey to ensure the seabed conditions were suitable for cable laying. This survey identified any potential obstacles and planned the optimal route for the cables. First end pull-in. The first end pull-in was initiated using a pre-installed messenger wire, which included an entry hole cover. This messenger wire was used to bring the pull-in line on board, connecting it to the cable pulling head. The Seam Amory is a state-of-the-art cable lay vessel designed specifically for submarine cable installation. It carried out the pre-lay inspection survey, first end pull-in, surface laying, Subsea crossings, installation of POO impact protection, and the second end pull-in. Detailed installation process. Surface laying. During the surface laying phase, the cable was laid on the seabed while ensuring accurate touchdown monitoring via a remotely operated vehicle, ROV. This phase involved laying the cable across Subsea crossings and applying POO impact protection to safeguard the cable. Cable cut calculations and marker application. On board the Seam Amory, precise cable cut calculations were performed to determine the required cable lengths. Cable markers were applied to indicate specific points, and their positions on the seabed were fixed. Second end pull-in. The second end pull-in commenced at 7 o'clock on the 28th, using another pre-installed messenger wire with an entry hole cover. The cable was fed from the cable tank and pulled from the foundation, engaging the cable protection system into the foundation. The cable pull-in continued with the assistance of a trenching ROV, which trenched the cable into the seabed for added protection. Technological advancements and efficiency. The Seam Moxie's 3D motion-compensated crane was particularly instrumental in handling the challenging offshore environment. Its man-riding capability ensured safe personnel transfers, while the ship-to-ship cargo transfer capability streamlined operations between the support vessel and the cable lay vessel. The comprehensive process, from pre-lay inspection to the final trenching of the cable, highlighted the efficiency and precision of the Siem Amory and Siem Moxie vessels. Their combined capabilities ensured that the submarine cable installation for the Nordsee 1 OWF was executed with a high degree of accuracy, safety, and reliability. The cable installation for the Gemini offshore wind park, one of the largest wind farms in the world, was a meticulous and multifaceted process, ensuring efficient energy transfer from the offshore turbines to the onshore grid. The installation began by connecting the cable to the land high-voltage station in Eemshaven, a crucial step for integrating the offshore wind-generated electricity into the national grid. In the shallow waters and tidal flats, specialized techniques were employed to ensure minimal environmental impact and maximum cable protection. One of the key operations was the use of the Nessie 2, a state-of-the-art cable burial tool, to securely bury the cable. This was particularly challenging in areas with existing underwater infrastructure, where the cable had to be carefully laid underneath pre-existing cables, requiring precision and advanced planning. Horizontal directional drilling, HDD, was employed to create a 550-meter-long conduit for the cables, ensuring a secure and unobtrusive passage from the shoreline to deeper waters. This method is less invasive, preserving the integrity of the seabed and minimizing environmental disruption. For the deep water sections, the cable-laying vessel Nexus played a pivotal role. The Nexus is specifically designed for such complex offshore operations, equipped with advanced technology to lay export cables accurately and efficiently. The vessel's capabilities were crucial for the Gemini project, which involved laying both export and infield cables across various depths and seabed conditions. In total, the Nexus laid 150 infield cables, connecting the individual wind turbines to each other and to the offshore substations. This intricate network ensures the optimal flow of electricity generated by the turbines before it is transmitted to the high-voltage station onshore.
The construction of a traditional lepa, a Malay wooden boat, is a methodical and highly skilled process that has been passed down through generations. Each step, from selecting the wood to assembling the final structure, requires precision and expertise. The dimensions of a lepa vary, typically ranging from 7 to 12 meters in length, with an average beam width of 1.5 to 1.9 meters. The choice of size depends on available materials and financial resources, as acquiring wood, especially for the keel, bow, and stern, can be costly if not locally sourced. The process begins with the keel, known as the tatas, which is carved from a single sturdy piece of wood. This foundational component determines the overall strength and balance of the boat. Once shaped, it is joined with the bow, tuja, and stern, tuja buli, which are constructed from matching left and right sections. The hull takes form when side strakes, or pangahapit, are attached, running along the length of the boat and secured to the bow and stern. These sections are locked into place with two long, precisely fitted side pieces called jungle. The jungle extends from the bow to the stern, forming a continuous structure that ends in a projecting bowsprit at the front and a small stern projection at the rear. To create the gunwale, a structural element that provides additional strength and stability, the first sideboard, known as the benkhole, is fitted above the strake and secured to the jungle. Above it, another sideboard, called the kapi is added. These boards are connected using wooden dowels, or pasak, which are traditionally crafted from durable mangrove wood. Unlike Western boat building methods, where internal ribs are installed early in the process, the LIPA's internal framework is added after the hull is fully assembled. This reverse method allows for a seamless, watertight exterior before reinforcing the inner structure. One of the most critical structural elements of the LEPA is the SAM, large, curved crossbeams that separate the bow and stern from the central living area. These beams are carved from the gelum tree, a species found in coastal regions. The SAM extend above the freeboard and later serve as attachment points for a rack-like branch called the panga. The panga holds essential fishing equipment such as spears, bamboo poles, and masts. Master carvers often embellish the SAM, bowsprit, and forward edge of the keel with intricate patterns, using a knife and wooden mallet. These carvings not only enhance the vessel's aesthetic appeal, but also signify craftsmanship and cultural identity. To reinforce the structure, additional cross beams known as sinkhole are installed across the hull. A central beam called the petarukan is positioned forward of the first sinkhole to support the mast. The number of sinkhole used depends on the boat's length, as these beams also serve as support for the decking planks. With the hull reinforced, the boat's freeboard is extended by securing extra boards called dinding, increasing both height and seaworthiness. These panels are connected using the same wooden dowel system, ensuring durability against harsh marine conditions. The central section of the LEPA, referred to as the balutu or kubu, functions as the primary living space. It occupies nearly half the boat's total length and is floored with removable decking or lantai. These planks allow easy access to storage compartments beneath the deck, where supplies and fishing hulls can be stowed. In contrast to the enclosed midsection, the bow, munda, and stern bully remain open and sit lower in the water. This design facilitates the handling of fishing nets and the use of oars and poles, reflecting the boat's practical role in maritime livelihoods. Durability is a key consideration in the construction of a LEPA. The most long-lasting components, the keel, bow, and stern, typically endure for the entire lifespan of the boat. Other elements, such as the sapau roofing, require replacement every few years due to exposure to the elements. Regular maintenance is essential, and at low tide, boats are careened and treated with fire. Using palm frond torches, builders heat the hull to harden the wood and provide an additional layer of protection against water damage. When sections of the boat are dismantled for repair, their joints are sealed with the inner bark of the gelum tree. This bark is known for its oily, water-resistant properties, making it an effective natural sealant. Boat operators also carry a supply of gelum bark aboard, allowing them to patch leaks while at sea if necessary.
When constructing a new dam or remediating an existing one, it is crucial to prevent water from flowing beneath the dam's foundation. If such seepage occurs, a barrier must be constructed to stop it. One of the most advanced methods for creating these barriers is the construction of a plastic diaphragm, slurry, wall. The process begins with the creation of a concrete guide wall along the dam's axis. This guide wall helps direct the subsequent excavation, which starts with a hydraulic grab that removes soil from the surface to a predetermined depth, typically up to 70 standard penetration test (SPT) units. These grabs are effective for digging through materials like clays, silts, and sands. Equipped with verticality sensors and flaps, the hydraulic grab ensures that the excavation remains vertical. During excavation, bentonite slurry, or mud, is added at the top to prevent the walls from collapsing. The initial section being excavated is known as the primary panel. After this, the grab moves to a new panel, and a trench cutter, hydromill, system is positioned in the pre-excavated primary panel. The trench cutter can cut through soils and hard materials such as rock, up to 200 megapascals, and can reach depths of up to 250 meters. A pump located between the cutter wheels transports the excavated material through hoses to the surface. The slurry, mixed with the cuttings, flows to a slurry recycling system where it is processed through shakers, desanders, and desilters. This closed system separates the bentonite slurry from the cuttings, rock and soil, allowing the cleaned slurry to be pumped back into the excavation. Maintaining a full slurry column is vital to prevent the freshly excavated panel from collapsing. Once the target depth is achieved, the trench cutter is removed, and the panel is prepared for backfilling with a cement bentonite mixture, which provides the necessary plasticity. This mixture has low permeability and low strength. After completing the first primary panel, another primary panel is excavated and backfilled in the same manner. Typically, panel thickness ranges from 0.6 to 1.5 meters, with grabs, also known as clamshells, capable of reaching depths up to 80 meters. Ensuring the verticality of the wall is essential, generally maintaining a verticality of 1%, although advanced technology and equipment controls can achieve verticalities of less than 0.5%. After the primary panels are in place, the secondary panels are constructed. The trench cutter overcuts the primary panels to ensure quality joints and a continuous wall. The overcut lengths are predetermined, based on the wall's thickness and depth. Once the secondary panel excavation is complete, it is backfilled in the same way as the primary panels. This process repeats, building primary panels first, followed by secondary panels, until the entire wall is complete. This method exemplifies the construction of a cutoff wall using a plastic diaphragm wall. Other techniques, like constructing walls with secant piles, can also be employed. These methods can be combined to create combi walls, incorporating secant pile walls within slurry walls. In critical situations where severe piping occurs, a grouting campaign might precede wall construction to minimize slurry loss during excavation. Regardless of the technique chosen, it is essential to establish a seepage barrier as quickly as possible to ensure the dam or reservoir operates safely. Ideally, these barriers should be constructed before building a new dam.
Abrajet hydroblasting is an industrial surface preparation process that utilizes high-pressure water mixed with abrasives to remove rust and paint from metal surfaces. Unlike traditional sandblasting, which generates significant amounts of airborne dust and debris, this method minimizes environmental contamination while ensuring precise and effective cleaning. The process operates at pressures ranging from 300 to 750 bars, allowing for controlled material removal without damaging the underlying structure. The procedure begins with the careful introduction of abrasive particles into a pressurized water stream. The selection of abrasives depends on the material being treated and the level of corrosion or coating thickness that needs to be removed. The water abrasive mixture is then forced through a high-performance nozzle designed to maximize efficiency while maintaining operator safety. As the jet impacts the surface, the abrasives break down layers of rust and old paint, while the water acts as a suppressor, reducing airborne contaminants that are common in dry blasting techniques. A key component of the Abrajet system is the specialized crossover nozzle, which is engineered to control both the direction and velocity of the water abrasive stream. This nozzle configuration ensures that cleaning is thorough and consistent, preventing uneven surface wear. Additionally, the system incorporates noise reduction technology, keeping operational sound levels at approximately 85 dBA, significantly lower than conventional abrasive blasting methods. This reduction in noise exposure enhances worker safety, making it a viable solution for long-duration projects in confined spaces or industrial environments where noise regulations are a concern. During operation, the system maintains a consistent flow rate to ensure uniform cleaning across large surface areas. The pressurized water assists in cooling the metal surface, preventing heat buildup that could lead to warping or microstructural damage. This cooling effect is particularly beneficial in applications involving thin-walled structures or precision-engineered components that require strict dimensional tolerances. Once the hydroblasting process is complete, the treated surface is left free of contaminants and ready for subsequent coating or protective treatment. Residual water and dislodged debris are collected and filtered to minimize environmental impact. This method is commonly used in shipbuilding, industrial equipment maintenance, and infrastructure restoration, where effective rust and paint removal is critical for long-term material durability.